Wonder what happened. Let's see. All right, says that we're live. Let me just update this. I wonder why YouTube did that. YouTube, what are you doing to me, buddy? I guess what can go wrong will go wrong. Let's make sure we all good. Looks like we're live. Looks like everything is. Yep, looks like everything is looking good. All right, so let's jump in. Let's jump in. Oh man, a long day. Sundays are always a long day. Always a long day. All right. All right, chat. Okay, let's just try to jump in. Okay, so this is a really interesting project for me. Um, this kind of started off really interestingly when I'm about to jump in, right? So basically, what I'm building right now, I kind of call it the engineered runtime, right? And basically, I was having a conversation the other day, and the conversation was around sub agents, right? And people launching hundreds of sub agents, and honestly, the math itself doesn't hold in terms of sub agents making you faster over time, right? Like, so the sub agents might be faster for tonight, right? Or if you're wanting something to be coded over the evening. But if you look at it over the long run, if your goal is to deliver a feature, your goal is to deliver some software that is a culmination of all these different features, right? Or all these different stories. Sub agents, if they're done incorrectly, actually make it actually longer, right? And it's actually more expensive. And it's a very simple fact of reliability engineering, right? If you take 10 components that all have to be correct in order to achieve a task, and each one of these components, let's say, are 95% likely to be successful, right? And in this case, I'm talking about an agent doing some work, working on a story, working on a work item, right? In your plan. If there's a 95% chance that it's going to get stuff right, right? And we're gonna come into that 95%. I'm gonna talk about that 95%. How do you get an AI agent to get your work item correctly, right? That you want built 95% of the time. No, that is an extremely high percentage, and you don't get it by chance. So part of this is what we're gonna walk for tonight in our architectural design decision records. But let's just assume that you can get it to work at 95% correctness. And if you have 10 agents that have to work on separate things to get that feature done, pure engineering liability math tells you that the probability of that thing being done correctly is 0.95 to the 10th power, which for those of us who don't like math, that is about 60%. So there is a 40% chance that the end product is going to be wrong. No. Here's the really interesting thing about this. If someone is following, they go like, well, Chris, fan out agents, right? You're running concurrent agents. It's more of a fan out pattern than a serial pattern, right? So someone might say, well, Chris, that doesn't hold because that's parallel, right? When I fan out agents, they're in parallel. But here's the thing: parallel agents are just costumes, right? Parallel agents are actually serial agents. Because the thing is that even if I launch 10 agents out in parallel, the fact of the matter is I still have to get them all done correctly in order to deliver the software, deliver the feature that I want to actually deliver. So at the end of the day, it falls under the same reliability engineering laws, which means that there's a 40% chance that this is going to be wrong. No, I'm not saying that fan out structure and sub agents working concurrently is not a good thing to do. Actually, it is. There's two things though that we have to get correct, right? For whenever we want to do that. One is how do we get the agents from, honestly, the 50-50 that it is right now for most people up to 95%. That takes a process, right? And then the second part of this is that within the process itself, how do we ensure that if an agent does the work incorrectly, it doesn't contribute so negatively to the entire calculation? Because just one agent getting this wrong can actually ruin your calculation. So how do you get your agents to just kind of like consistently get to 95%? That is where this whole conversation started. And I said to myself, well, in order to do that, one of the reasons why I get a really high level of success on my agents is because I have a process, right? And that process, I'm start calling it an engineered runtime, right? And it definitely takes a few steps. So it occurred to me, why don't I build this as an actual runtime? Why don't I build it into something that any project that I have, right? I can jump into Cloud Code and it is actually going to execute that for me. And when I say execute that for me, I mean everything from ideation all the way to actually deploying software. So I'm actually going to show you something. We'll kind of like bring everything to a little bit, how should I say it? Something that will actually make all this kind of like illustrative. So let's look at this. So this is just the stream. Yeah. So this is what I'm actually building. This is the engineering runtime pipeline, right? So this is exactly what I'm building. It's called engineering runtime pipeline. I'm going to zoom in a little bit. And the idea here, right, is that I can follow all these steps to be able to deploy solutions, right, agentic driven solutions at a very, very high reliability rate. Okay. But it definitely takes a few steps. So just imagine, can I turn this into a runtime that I can give to anyone and they would actually have the success that I have? And even at the same time, can I develop this such in a way that every one of my projects are going to follow this approach? So to be very, very clear, this is an engineered runtime for agentic coding, right? And then this is how it works at a very high level. The idea here, and I think it was Andrew, I mess up his always mess up his last name, Andrew Kanaski or whatever, right? I mean, a ton of people follow him. He mentioned something this week that I've been doing forever, right? I actually just have conversations with my LLM all the time in terms of projects I'm going to develop. So my first step is always conversations. It's not writing something down. I just actually go on a walk. I jump in the car. I just have long conversations with my LLM, right? And the reason that he said that works is because there's so much context that actually you miss that the LLM needs when you kind of write things out. So it says, look, just blabber to it. And the thing is, we couldn't do that before because of token sizes and cost and all that kind of stuff. But now we can. So something I've been doing for about like 6 to 9 months, he's now saying that this is how he works, right? And I think he's been working like this forever. So really what that means is the process for new software, right? For new application that you're going to do some agentic coding with, right? And anyone who follows me know I don't like the term vibe coding. I use the term software composing or agentic composing because it's definitely engineering, right? I don't do YOLO, right? I'm doing actual development for products that could actually go out, right? In healthcare, in fintech, right? Transportation and logistics. So this is not about YOLO, right? This is about going from, let's say, from YOLO to actually real production systems that you're going to develop, production applications. And I'm telling you, the first thing that starts up with is a conversation. And that conversation can be had a bunch of ways. I can have that conversation for example, just as I mentioned, me talking to my AI, or it could be a conversation where I'm talking to clients and they're just transcripts of meetings. As a matter of fact, one of the most favorite things that's one of the favorite things I do. I grab all the transcripts that I have from all the meetings. I talk to the users, I talk to the clients, and I feed it to my LLM. So that's the first step. So you drop that conversation in to your LLM, right? And the way it's going to work when I'm done with this, right? And again, I think I need to really say this. This workflow, this engineered runtime, what it's meant to do in one line, it is meant to allow a developer to actually have agents write code autonomously, right? So you have YOLO development, which is like, oh, I want this application to do this, go do this. And then you have real agentic composing, which is I'm going to go through a process, and when I'm done with it, the artifacts that I have from that process, I can walk away for 10, 20 hours, and what's going to be developed, right, has a high probability of being exactly what I wanted. And let's go back to the reliability engineering math, right? To And I remember I said you have to have two things to make sure that comes out correctly. The sub agents have to be able to produce the outcome for each ticket, each work item at a very high probability. Right? Remember I mentioned that. Because when you chain them together, a 95% probability of success chained together 10 times, only a 60% probability of the entire thing being correct. So how do you get right? So how do you get that 95%? How do you get that 99%? Well, it's tough because 99%, right? When working with an LLM, you're not gonna get that by just simply just doing the thing one time. So the way you actually do this is you want to make sure that the information that you give to the LLMs, right, they're correct. You have to make sure that you're breaking down information into like nice atomic pieces, right? You have to make sure there's testing, right, along the way, right? And all those things. So this is what this is. The engineered runtime is going to include all of that. And you can imagine how this is going to work if someone jumps into their Claude code, they hit slash initialize, and when they hit slash initialize, the LM says to them, hey, do you want to have the conversation right now, or do you have the conversation already? The person goes like, yep, here's my transcripts, here's all my documents. Oh, and by the way, let's just have some conversation about it at the same time. It could be anything that they want to do. It could be conversations with Claude Code. It could be conversation that they had already for transcripts. It could be anything. Slash initialize is going to get that. What slash initialize is also going to do is going to actually it's also going to initialize a few configurations. And I'll get into that a little bit later on. But some of the configurations are going to be things like, hey, what models do you want to use for different tasks and all that stuff, and the LLM will actually recommend and all that stuff. But keeping what I'm doing here, I'm initializing a project with the idea of at the end of the day, my agents are going to run autonomously, and I want at least a 70, 80 to 80% chance that if I walk away for 10 hours and I come back, the system that I meant to develop is the system that I actually get. This is what this is all about. Okay, so if you look at this, so you can look at the conversation stats off here. Then the second part is that from the conversations, you're going to get something that's really, really, really super important, right? You're going to get ADRs, right? And ADRs are architectural decision records, right? And if you haven't really seen ADRs yet, this is the first time you might be seeing them. I think they're the most awesome things that you can actually do. I do not do any development without these records, right? I just don't do any development without these records. It's like super important for me to do that kind of development, right? Actually, let me bring back up the screen back up. Why is this the screen that's actually showing? That's actually weird. Let's see. Do, 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 do. Why is it showing the live streaming screen? That's so weird. All right, so yeah, I'm back. All right, so these are the ADRs, right? Architectural design records. And the thing about architectural design records, let me zoom in a little bit, right, is they really drive the whole direction of what you're actually developing, right? They drive the whole direction of what you're developing, and they're going to contain all the information for all the important decisions that you're making about the application that you're going to build. Everything from infrastructure, memory management, scaling, right? What platforms that you want to use, DevOps. All of this is in the ADRs because that's the first thing that you want to do. You say, this is what I want to build, and here are the important decisions I'm going to make, the architectural decisions that's going, and the design decisions are going to drive everything. So it's the first thing in the process. And you can imagine with the engineering runtime, you do not want as a developer to actually sit down and write those. So in the engineering runtime I'm developing from the conversation, these are actually then created automatically, right? Now, once these ADRs are created, the next thing that's going to happen is you're going to come into what I call story arcs, right? So story arcs are going to be, some people call them epics, but they are demonstrable slices of what you're trying to build, right? So for example, if I'm building out, you know, let me come up with an idea. I mean, there's a ton of stuff I'm building. Let's say I'm building a document platform for law firms, right? Story arc, one story arc might be authentication. The next story arc might be how we use AI to handle document ingestion and extraction of data, right? So this is like this big epics, these big story arcs. Now, these story arcs I don't want to actually do, the engineering runtime will do for me, right? So it goes from conversation to ADR, the story arcs actually kick in. And behind the scenes for the story arcs, what happened is that the LLM is going to already have configurations for my project from initialize. It knows what type of project it is. It knows how long that I have. It knows a ton of stuff. So it's going to actually put them together in story arcs, right? And then the next thing it's going to do is then it's going to take those story arcs and it's going to break them down into different PRDs, right? Which is just a breakdown of what and how. So again, what you see us doing is going from transcript all the way down now to going like, okay, ADRs is how we're going to actually do it from a design standpoint, right? Then we go into to story arcs, like, okay, cool. What are the major things that we're doing? Then it's going to jump into the PRDs, which is going to be like, okay, cool. What and why are we doing each of these story arcs? And I'll give you a little bit of a teaser why I'm doing this, because at the end of the day, I want to end up with something very small that's going to be super important. Now, from the PRDs, we then do specification documents. And some specification documents are how we actually do something, right? So think about what we came here from. We came from a conversation that we just initialized all the way down now to specification files, which is how we actually do those things. Very, very specific. All that came from the ADRs. So ADRs are super important, right? Then in this system, we're going to come down here to node contracts. So this is where it gets really interesting, right? Because what I want to do, right? What I want to do is after I get to the specs, right? I'm going to get down to this node, to this sort of this node contracts, and these node contracts are going to be super, super important for the rest of my process, right? So I'm just going to bring something up here on my end. Right? So again, the node contracts are small bounded work packages, right? And it's important to understand that because each has to pass an admission check before they enter the plan. So one agent will then write the test that will judge the work. A second agent will write the implementation, and there's a controller that will run the checks and decide whether it succeeded, right? So you can see all that, right? So node contracts, you have a DoD admission. This is actually pretty cool. The DoD's definition of done. So what's going to happen is that whenever you initialize in the beginning here, the AI is going to recommend you a definition of done. So for those of us that don't know, definition of done comes from Agile, and definition of done is just a really kind of like a really strict contract, so to speak, right? It's like a really it's a contract, right, as to what it means to what to define your project or your feature or the story you're working on as done. So that would have already been done in initialization, and it would have been recommended by the LLM based on the project that you're doing because it has your whole transcript. You'll approve it, you might tweak it, but then you'll have a DoD. So basically, you create the node contracts, right, which is the bounded work packages. DoD then actually kicks in, right? Then you have test nodes, right, that are going to get written, and they get written in a different context from what actually created the node contracts. So basically, they're independent, right? So that means that AI can't cheat. Then you're going to have the workers themselves that are actually going to do the work, and you're going to have evidence, different evidence workers that's going to make ensure that the work that the AI said it did is actually done. So that's evidence, right? After that, you're going to merge, run, and branch. And then, most importantly, when I get up in the morning, I will get a morning report of actually what happened the night before. I can then simply just go through and then use accept and reject, um, sort of like commands. And in that way, it actually pushes up my code and stuff like that. So at the end of the day, what I'm designing here is a system that replicates how experienced developers work. It is a system that replicates how I work. And it actually then takes it to a next level because I'm not consistent with it, right? And also there's some things that I actually skip. No, I am really underselling all of this because within here, right, in within each of these nodes in the system is some awesomeness, right? So for example, let's look at the test node, right? This test node does more than just perform tests, right? In terms of how you know it, this test node writes the unit, right? This test node offers the unit test, right? This test node red teams the unit test. This it also does traceability audits on the test, and traceability audits help you figure out what did you miss. Red teaming makes you figure out, hey, are my tests strong enough? Right? It selects obviously the right library that you want to use to actually run the test. And one of the cool things about all of this is that this test node doesn't exist at the beginning of the actual run. These test nodes get created on the fly as sub agents when they're needed, and they actually perform the job of gating the development. Remember when I say that, how do you get 95% reliability from an agent? It's by this introduction of this test node. This test node will force the AI, right, to rewrite the bonded work packages, right? Test them against the DoD, make sure the worker is actually doing its job, and it will only make it past the gate after the test node has been satisfied. And here's what the cool thing about the test node is: the test node is not AI. The test node always written by AI, it's fully deterministic. And even the AI that actually writes the test node, right, has its own context. So it has no need to lie, right? So this here at the bit at in the middle drives so much, right? So this test node itself, and I'll just zoom in a little bit. This test node itself is central, and one of the things I cannot exaggerate enough is that the fact that this test node does not exist until the actual sub agent actually runs. And one of the real cool things to understand is that this worker, this sub agent, it is working on the smallest unit of work it can do within the system. Remember how we started off with the conversations when of PRDs and specs and the node contracts, which is the bonded work packages. These bonded work packages, they actually have a limiter. The LLM does a calculation based on the engineering runtime, and it calculates, so it makes an estimate of how many tokens will be used to actually solve and build out this work package. Because one of the things that you want to do from a cost standpoint is, once you get to 100,000 tokens, 150,000 tokens, you start getting very inefficient with cost, right? So one of the things that the node contracts do is, at the beginning of the conversation, right? And so after the conversation, the system will actually, when it initializes the system, it will ask you, hey, do you want to use the standard node bonded work package, which is 100,000 tokens, or do you want to increase it? It'll actually give you a recommendation, right? So the way I'm building this is that most likely you'll say yes, right? And then obviously from that, you're able to say, okay, cool. If I have 100,000 tokens, and you can say, well, okay, cool. I know what specifications I have to write, and I am going to write the specifications into work items, which is Kanban terms, small enough that I don't consume more than 100,000 tokens whenever I work on them. Now, this is a departure from how work is scoped for human beings, right? Work for scope for you is not scope for human beings by tokens, right? But in this new age of what we do agentic development, definitely token usage and the amount of tokens you use should be the way that you scope because you can, right? So basically, once you actually go through all this, as I mentioned, you merge, you get a morning report, you accept, and you actually decline. So at the high level, this is what's being built. I will say one thing before I actually jump into looking at at one of the ADRs is this, and I do not want to undersell this because this is actually at the heart of all of this. Right now, when people do sub agents, right? So let me just kind of switch back to the screen here. Right now, when people do sub agents, what they actually do is that they just break down this work that they have to do in smaller pieces just arbitrarily, or they actually ask the LLM to do it for them. The problem is I already showed you the math on this. If you do this wrong, the probability of you having success at the end is ridiculously low. And if you don't think 60% is low, I'm going to show you the next piece of math. Remember, I only did the 0.95 to the 10th power. Like if you had 10 sub-agents, and I say it's only a 60% chance of actually finishing properly. People don't launch 20 sub-agents. They launch 20. Sorry, they don't launch 10. They launch 20. They launch 50. You know what the math is? 0.95 to the 50th power. Do you know what that math is? 7.7%. 8%. There is an 8% chance of your project being delivered, or the feature that you're developing being done correctly. If you have a 95% reliability on every sub agent, on every piece of work, you have only an 8% chance that the output is actually correct. Crazy, right? And here's the deal. We don't do 95%. Nobody's agents do 95% if you don't have a good process. And this is what we're talking about here right now, is a proper process, right? So, and then the other thing that actually really matters is this, and this is really core to this engineering runtime that I'm actually building. Even the check-in of the agents as to whether they're correct or not is done wrong in 95% of sub-agent fanouts. Most of them are wrong. Because here's the thing, there's no gates, right? There's no gates. And even more so, what we need to understand is whenever we have work items in a project, there's dependencies between the projects, between the work items. So that means it gets worse. It means that if I am doing fanouts, which is just serial development disguise, that's all it is, I have to understand that there's dependencies all over the place. One item has to be done before another item, right? And all that kind of stuff. And most fan out structures or fan out sub agent structures, or how people do it, they do not take that into account. So integration, merging are nightmares. So you say, well, Chris, how do you solve this? Here's the deal. And this is what's going to be cool about this engineering runtime. It's going to use a sequencing engine along with DAG. It's gonna use, right? It's gonna use DAG, a directed eclectic graph, right? Which actually has all relationships in it. So we'll be able to show the relationships between actual work items and the sequence diagram, which is gonna allow us to overwrite the property of DAG, which is that it's only in one direction. So like you do from one story to one work item to another. With sequencing, we can then on the fly kind of change that. That's going to be at the center of this entire engineering runtime. So what does that mean? It means something very special. It means that after you've gone through this process that I'm showing you here, and you've created all your work items, right? Your work items are the little pieces of, let's just call them little feature. Like, not, I won't call them features. They're wrong. Work items are just stories for some people. They call it, but it's the little things that you have to do, right? Like write this function, create this, right? Like write this API endpoint, create this database table, stuff like that. What you understand here is that all these things have dependencies on each other. And whenever people do sub agents, they usually not taking into account all the dependencies and all the reliability checking. Because if one dependency gets it wrong, then everything else in the chain is wrong and all that kind of stuff, right? So basically, at the end of the day, with DAG and sequencing, the engineered runtime is going to be able, listen to me on this one, is going to be able to smartly look at all the work items in the plan and create a DAG, like a graph. Sure, right? And when it does that, it will create the DAG based on what kind of configuration you want. So you can actually say, I'm going to create me a DAG of all these work items for speed. So then in that case, it'll over-index for speed, right? So over-indexing for speed might mean more smaller work items and all that stuff. Or you might say over-index for cost, right? For cost, since you know that the more work items you have, the more sub agents that you have, it's the increased chance that you're going to actually fill packaging everything together, right? So if it knows that, it'll say, okay, cool. If I want to over index for cost, I'm going to reduce the number of sub agents that I'm going to do. It's like simple engineering reliability math, right? But the DAG, right, the graph is going to be drawn, and that DAG will be known and stored, right, in the database, and the LLM will know, and it's going to use that to then actually then create, right, the plan for the sub agent fan outs. So it's going to be super efficient, right? So just listen to what I'm telling you here. It came from an idea. This engineered runtime is going to break it down into ADRs. It's going to go into PRDs, specification files. It's going to write smaller work items, right, that are written and estimated will not go past 100,000 tokens. At the same time, it is actually looking at the graph, right? And it's obeying the rules from the graph. So then when it writes the plan, it has all the dependencies. And based on that, it actually writes the tests, it writes the gates. And that's how you can actually then, after you've gone through that process, go to bed at night for 8, 10 hours or whatever and say, hey, go launch this 100 sub agents. And the system itself will most likely not run all 100 sub agents at a time if that's what it takes. Like if you have 100 work items, it won't run 100 sub agents at a time. It will use the graph to be able to launch the right sub agents at the right time. In certain cases, a sub agent cannot launch, right, unless if, right, a test node approves it for deterministic test. So the AIs cannot lie and say that they actually did it. All these things are separated. So think about what's happening here. If I go to bed and I have 100 work items that have to be done, I am not making the decisions of launching 100 sub agents. The engineering runtime is going to efficiently, based on the graph, launch them. I want to be very clear again what's also happening here. I'm also telling you that the engineering runtime, these sub agents are going to be smart enough to know when to wake up, when to proceed, when to go back to sleep, if they're still gated. That's what I'm talking about. This system is going to be smart enough to know and to change the plan on the fly. So something you might assume something can be done, and when it's time to actually do it, the plan that you had from the specification file is wrong. It has to do something else. It's going to be smart enough to then change the stories that depend on it, and it's going to know what its boundary is. And its boundary is the architectural decision records. It will not do anything that the ADR says do not do. So it will the ADRs provide the box. So when the agents that are actually doing their work, yes, they'll try to follow the specification files, right? But and obviously they have a definition of done. So the definition of done is the goal. It says, hey, I have to do this. The ADR will say, well, it's kind of like policy says you cannot do X, Y, and Z because we've looked at it before and we've actually sort of like crossed it out. And based on that, the agents now have their goal and they can do what they need to do in the runtime. And they can change the dependency graph and all that kind of stuff. So when you get up tomorrow morning, the chances that you actually have a feature that is shipped from your 100 work items is actually going to pass because what you need to do is pass the definition of done. Now, so I know this is a little bit heavy, right? So you understand what definition of done is, right? Understand what acceptance criteria are. All these are like agile terms that have to do with development. And if anybody has any questions on those terms, right, drop them in the comments. All right, I'll be sure to actually answer. Even if you're looking at this after the live, I'll be checking this here. I'll actually answer the questions. What is definition of done? What is acceptance criteria? All those things, right? We can actually go into those details. So with that being said, there are 32 ADRs, architectural decision records, that I have that governs the system I'm about to build. So obviously, this is like eating its own dog food, right? So the system is built to create ADRs as part of this process. So obviously, remember I said that that's what I do myself when I develop ADRs. So in developing the engineered runtime, I use ADRs. There are 32 ADRs that I'm actually created. I've created, right? And those ADRs came from conversation with the LLM. The same thing that I'm actually encoding into this runtime that I'm building. Again, eating my own dog food, right? So basically what's going to happen here is I'm going to do 32 episodes of this stream, right? I'm committing to do that. It's going to be an hour a day. This one is a little bit longer, but it's going to be like an hour a day. I have to determine what time I'm going to do it. I'll kind of let the community know, let all my subscribers know, but I'm committing to do an hour a day. And every day we're going to go through each one of, we're going to go through one architectural decision record. I'm going to show you what it does. You're going to see me actually read through it. You're going to see me evaluate it, right? You're going to see me possibly make changes to it. You'll hear my thought process on why I'm doing certain things. Because understand this, I didn't write these ADRs, right? I have a skill that writes these ADRs. It knows what I need in the ADRs, but I did not write it. It came from conversations with the LLM and from transcripts and other things I give it. And it says, based on these are the ADRs that you actually need. So I'm actually putting my eyes on them for the first time to ensure that the decisions that are being made are in line with what I had the conversation with the LLM about. And the reason why this is so important is I kind of explained it already. The ADRs provide everything downstream. It's from the ADRs we actually create PRDs, specification files, right? Work items. It's the ADRs that actually serve as guardrails when the sub agents are working and they realize that the plan that we had for a particular work item doesn't work. It's the ADRs that go like, yeah, you can do, right? Like this is what we decided that we're not doing, so you cannot do it, but you can do everything else, right? So the ADRs are extremely important. So every time I develop a system, I spend a considerable time on ADRs. And here's the other thing I want to actually mention. The engineering runtime is so I can create autonomous agents for coding. The one way I can have faith in these autonomous agents is if the entire thing on which they're building upon, I have looked at them. So I am not going to sit down here for 10 to 12 hours to look at agents code. I don't do that. As a matter of fact, my agents code mostly at night. I go to bed, 12 o'clock, right? I go like, hey, here's your work items for the night, right? It's 100 work items. Go do your thing. I'm not sitting here watching code being written. I know a lot of people do that. But I do spend on every project that I have about an hour and a half on ADRs for each project every day, right? In the planning phase. And when I come in the next morning, I might update ADRs, right? Which will then trickle down to update PRDs and specification files and work items. But the driver of all this is the architectural design, right? Architectural decision record. That is it. I will preach about ADRs every single day because this is what allows me to deliver agentic coding agentic coded software at a ridiculous rate and at a ridiculous quality. So I'm sharing this with everyone. All right. So with that being said, let's jump into our first ADR that we're gonna review out of the 32 ADRs that we're gonna do, and this one is gonna be ADR4. And this is gonna talk about why ADR4 is important, and you can see it in front of you. And I started with ADR4 because it is the most important ADR of all, right? So as you can see, ADR4 is related to ADR9, ADR10, and ADR15. The other thing I'll actually mention too as well is this. ADRs are pretty small. ADRs are named properly, right? And I usually have an index of ADRs. And why I have that is because then I put that into the cloud.md file so that my LLM, when I'm creating PRDs and specification files, it's always loaded into its context. Not all the ADRs, but the titles. So it knows what ADR it could possibly look at for a particular PRD that it's doing, or a particular specification document or file that it's doing. So I have an index of ADRs. The ADRs are named properly. And if you look at a general high level anatomy of an ADR, it is the context is like, hey, why do I need this ADR? Then it has the decision. It says this is a decision that I'm making in this ADR, right? Then it says, okay, what would the alternatives considered? Right? It says, okay, I'm making this decision. The alternatives I considered were this. Here's why I did not take them. Then it says, here's the consequences of the decision that we made, positive and negative. And there's also a line that says that we might revisit this if this happens. And then it has a link to the other ADRs. Why is all this important? Imagine a sub agent is working, right? It's looking at something and it's trying to code it. The work items, right, point back to the ADR as well when the sub agent is working on it. It reads the context. It says, okay, this decision affects me and what I'm working on. It says, oh, okay, I get it. Here's all this detail. It says, okay, I get it. Here's the other alternatives. So it says that, okay, these have been passed on, so I cannot do those in case I'm thinking about drifting, right? Because agents drift. So he says, I cannot drift. This is what prevents drift, right? All of this prevents drift. And then the area of some, and sometimes your agent sometimes will kind of be really chatty and be like, okay, do if this is why you're doing this, this is the negative. It goes like, oh, I know all of this already. Oh, all of this is in the decision record already. And the agent will also pull up related ADRs, so it has it within its context when it's working on the work item. See how that kind of works? So it's almost like a policy guardrail, but it's also like a little bit of semantic memory, right? In terms of this is how we do things and why we do it, because something your agent needs that sometimes for its reasoning. So again, ID, title, status, date, deciders, related to, right? And the first thing here for ADR4, you'll see that the context of ADR4 is that it is the load bearing decision of the entire system. Right? It is load bearing for the entire system. So this is why I'm doing ADR4 first, because it is load bearing for the entire system. All right, so I'm going to pull something up. So pretty much, I'm going to show you a next diagram too as well. So I just want to kind of show you this. So pretty much what it actually comes down to, and this whole system is based on this. LLMs will claim that they've done a job all the time. And a lot of times what people do is that they'll put tests in, and this test has to be done by the same process that actually produced the work. Means that they're both going to have the same misunderstanding, and they're going to have a strong prior, right, towards reporting a success. So what that means is that they're both going to be inclined to report success. See, because a worker, right, we talked about these. Let me show you a worker right here in the system, right? It's right here. A worker can genuinely think that it ran the test. And If you've done any agentic coding, you know what I'm talking about. It happens all the time, right? A worker can genuinely feel that it think that it actually does the test. So there's a governing principle that I have from a broader production AI Bible that I wrote, is that I always take away an agent's vote whenever that answer can be determined by code or fudged by the agent. In other words, what I'm telling you is, why would I want the LLM, the agent, the sub agent that worked on a particular work item, why would I want it to actually have anything to do with testing the work that it just did? Why would I want any sub agent, which is probabilistic, to test work that another probabilistic sub agent just did? I don't. That has to be something that's deterministic. And we already have that in our toolkit if we're developers, right? What we have is the ability to write like unit tests. So then it becomes now I need to introduce a new node in this entire in the graph. Remember, I said this is all a graph, right? This cannot be lost on anyone here, right? The engineered runtime, what it produces after it goes through everything on the top here: conversation, ADR, story arcs, PRD, specs, right? What it creates is a graph, and in the graph there are nodes, and those nodes are test nodes and worker nodes. Worker nodes write code. Test nodes make sure that worker nodes did their job. Right? Test nodes know everything about definition of done. Worker nodes know everything about the node contracts. The test nodes do as well. Right? Worker nodes, in terms of a graph, do not talk to worker nodes. Worker nodes are only connected to test nodes. They're gates in a graph. And test nodes represent dependency. And the only way the dependency is actually met is when evidence is produced. This is the beauty of the whole system. And obviously, the additional beauty is that these nodes are actually created on the fly. Sometimes they can actually change based on the things that are changing as the worker actually sees them, all within the confines of the ADR and specification files. Right? This gets a little bit more complicated, but that's kind of like the idea that you have here, right? So basically, the whole crux of the system and the reliability engineering calculation is about how can I get a sub agent to deliver according to my definition of done and hit my acceptance criteria on the work item at 100%. That's what it's all been about. How can I get it to 100%? Because if I'm running 50 sub agents and they're all at 100%, my outcome, which is the feature or whatever I'm developing, is at 100%. That's what this is all about. This is the load bearing of ADR for the entire system. Because if I cannot get the agents to reliably work at 100%, my outcome is garbage, right? I'm going to be delivering stuff properly at 60% of the time, doing a bunch of rework and all that stuff. And remember, that is what the big deal is. So I actually want to show a little diagram. So basically, all this again is going to be part of the runtime. Again, I do all these things for skills and all that kind of stuff, right? So whenever I do an ADR, one of the things I do with ADR is that I have my skills generate me diagrams, right? Because pictures worth 1,000 words. So let's just kind of look at one of the diagrams that actually go along with this that the AI actually gave me. And again, I haven't seen this yet. I'm doing this live with you, like I'll be doing with myself. So I have a false premise cache. So let's see what it looks like. Okay, so I'm gonna take this. Let's drop this over here. All right, so let's see what we got. Let's see what we got. All right. Because I actually do this, I can zoom in a little bit. So yeah, basically what this is basically showing me what that looks like, right, in a normal system. So in a normal system, node A says I'm done, right? So it's a generated token sequence. Generate token sequence is a fancy thing of saying that it did the work that it was supposed to do, right? So it says, hey, I'm done. If you're having the AI also test its own work or any other sub agent that's also deterministic, it might actually be that it generally did it. It genuinely did this, right? Now, if I'm looking at work done in a sequence, as we've been talking about, it's bad, right? Because node B starts from a false premise, and then node C inherits the false premise, and then you have three nodes of rework. And this is the part that you cannot actually skip. At this point, you're done, and you get up next morning, and if node A was wrong, node B is wrong, node C is wrong. And remember, each of these nodes represent a work item, right, in Kanban. So basically, a piece of code that you have to write. You get up tomorrow morning and you had three of these agents running in sequence, and node A was wrong, node B is going to be wrong, node C is going to be wrong. You're going to have your agent rewrite all this code. Not efficient, expensive, and takes a long time. Now, let's look at how that looks like in a fan out. Right? So in a fan out, same thing happens. Node A says I'm done because it was the dependency for node B, node C, node D, and node E. Right? No gate, you had no gate. The fan out happens. Node B is building at the same time of node C, node D, and node E, and the rest of that wave. They then actually converge when all the work is done. Here's the problem: integration and convergence is going to be wrong because node A was wrong. But it also could be wrong if node B, node C, node D, or node E is wrong. See the dependency? Node A is wrong, everything is wrong because it was a dependency, right, of all the others. If any one of these, think of it like an or. If any one of these are wrong, the convergence is always wrong because these have not been gated. And even if it's a 95% chance that they're going to be done correctly, again, nobody does 95% correctness with the AI coding tools. It doesn't happen, right? When if you put them against a story, a work item the first time, you have to actually have a way that they get retried, which is what this entire runtime is about. So that's why fan out is reckless everywhere. But in our system, it's not because we have the test nodes that are deterministic that will actually block these things from happening. Right? So you can see that. So you have sequence, problem, parallel, problem. And I would actually tell you that the parallel problem is actually even bigger because you're doing all the same things at the same time. Right? So that's kind of like why ADR 4 is super important because we want to be able to take away the agent's vote in determining whether its code is okay. And we want to push it out to a testing node, right? So basically, you see what the decision was here. The decision is that agents act, but evidence advances. And you can actually see that in the diagram here. Agents act, right? Workers do their thing, but evidence is the gate to advancing. So that's the rule. So, and then you can see what the ADR says. A worker's completion claim moves its node from running to verifying. So, right, so when a worker is completed, a sub agent is done, it will move its node in the graph from running to verifying. And it sends out a request for adjudication, and it doesn't do a state transition, right? Because remember, this is a graph. So, right, along with sequencing, right? So it says, hey, I am going to change information about myself in the graph, but I cannot change my state, right? So then there's a controller that then executes the validators declared in the node contract, right? So the sub agent is a node. That node has a contract. Within that contract, there's a validator in that contract. So each produces a durable evidence record, meaning that a durable evidence record means it's something that's actually going to get saved, right? It's going to have the validator identity, like who actually did the validation, the structured outcome record, captured output hash, a base commit, a result commit, a timestamp, and a graph version. Only when every required value passes does the controller transition the node to pass. So what I'm saying here is that not only am I, it's not that there's one test node. You can have multiple test nodes attached to a worker node. And what it's saying here is that because it's a graph, I could then have test nodes, right, where one test node is a dependency of all the other test nodes, and I can have them in chains. I can have them in all kind of relationships to them, between themselves. And the cool thing is that it's when at the time of creating the work item, the engineering runtime will determine all of that based on how you tell it you want the graph to be created. So again, you can see whenever you create a node in the graph, the node has all the validators, which is basically it knows all the different nodes, test nodes, that actually have to come back as true for it to be able to change its state from required to pass, which is a really beautiful thing. So you can see I was working through here when I was talking to the LLM, and you see there was an addendum. It was amended, right? Because guess what? I do red teaming on all my ADR conversations, right? So all my LM conversations, I red team after I actually talk to the LLM before right. So I'll write a version of the ADR. Then before I even read it, I will say to a to multiple sub agents in a red team, go ahead and attack this, right? So basically, when I run red teaming against this, it came back and it changed a few things, right? So it basically says that hey, if something exits, like we're going to use PyTest. So if you get an exit zero, right, it means that no test fail. It does not mean the getting test pass, which is a very important thing because that would have been a hole in the system, right? Because if you say an exit zero means that you passed, you're like, that's not true. Exit zero just means no test failed, which is not the same thing as the getting test pass, right? So a skip test exit zero, right? So in PyTest, it appears that if you skip a test, you have a zero, right? And the value of the process is not independent of the work it judges. The runner imports the implementer's code. So implementer offered code executes inside the controller's own validation run, right? And you can see what that kind of looks like. Therefore, for any value that acts as a node gate, and this is important, so I got to stop and read this because remember, this is the first time I'm reading this, right? I'm reading this along with you. This is me doing my process with you, right? I haven't seen this before. So I'll just pause here myself to kind of read. Therefore, for any validator that acts as a nodes gate, okay, that makes sense. So any validator that acts as a nodes gate. Let me show you what that means. So for again, the test node here will gate the worker, right? For it to be completed. And you can have multiple of these test nodes in the configuration for that worker. So that's what that means. So far, so good. The evidence, so it says, for any validator that acts as a nodes gate, the evidence artifact is a machine readable outcome report. So that makes us about a bunch of sense, right? So because we want obviously our we have code that's going to read it. So for example, we're going to use JUnit XML, PyTest JSON report, or the runner's equivalent, not an exit code and not capture text, which is actually pretty cool. It says like, look, so anything that's kind of like just exit codes, these are not artifacts. Artifacts must come in the form of a machine readable outcome report. Great. The second thing it says that the controller asserts identity, not aggregate. The exact test IDs collected at red check time must be present in the report with outcome equals passed. The exact test IDs collected at red check time must be presented at pass. So it's referring to ADR 20. So let me just read that a little bit because I'm a little bit confused by that statement. So let me see what that means. All right, so this is ADR 20. Now I was gonna do a search here for red check. Let me see. Hmm. let me see. Okay, there you go. Okay, so it says here that a test node's gate is not a file exists. It is the new test executes. A test node's gate is not of it is. It fails against the scaffolded tree. It fails for the stated reasons. The collected test IDs are recorded on the node and become the must test IDs, must pass test IDs, but the implementation node's test report validation, blah, blah. This is what makes the gate unskippable later. The same task photo provided red by name must later be proven green by name. Oh, okay. I understand what that means. Okay, that makes a ton of sense. So let me go back. All right, that makes sense. So I'll kind of like explain what that means. So let's kind of read that again. Don't worry. The controller asserts identity, not aggregate. The exact test IDs collected at red check time must be present in the report. So basically, it basically says like, look, you don't get right. Look at this table. It says it asserts identity, not aggregate. The most important part here is not aggregate, because the controller, which is what runs all of this, right, is basically saying that, look, I know you can rerun those checks, and that's great, but you don't get to do a new check, even if it's on the same thing, and it passes and be like, hey, that passes. It says, no, 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 no. When I did a red check, right? Because there's a you red checking, you're kind of red teaming, you're testing things for failures and all that stuff. It says the IDs collected red check when things failed must be present in the report with outcome equals pass. It basically says I'm not aggregating stuff here. When the test gets generated, those text IDs are unique because they represent things that actually have to get done. If you fail and it has to, you are the LLM, right? You kick it back to the worker, so the LLM checks its code and fixes it. When you come to run it again, those test IDs are unique because the tests are unique, right? You need to show me that you passed the same test again. Maybe there's new tests that have been added, but those tests that you failed previously, you need to run them again. That's what that means. So that's actually pretty cool. Then it says skip, exfil, and absence are hard validated failures, not neutral outcomes. A given test that did not run has not passed. So that actually makes sense, right? We don't get to skip tests. Exit code and std out are still captured as context. They are never the verdict, right? So basically, all this basically says is that, and I think why it's doing this is sometimes you can get exit codes, and exit codes can be like a little bit misinterpreted, and sometimes you have standard output, right? And the LM can maybe look at it and kind of make some strange inference and all that stuff. He said, I know this is not a verdict. First of all, earlier on here, we said that no, 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 no. We said that you're going to give me JUnit XML. So if you give me an exit code and you just give me standard output, I don't really care about that. So this is the same lesson as spike finding E8. So for those who don't know what a spike is, whenever you do a project, there's some assumptions that you have. Before you get into coding it, you can do a spike. And a spike is you can create a series of stories that you actually have to do. And those stories are just going to be to test an assumption, right? So one of the things I do in my process is that I always do spikes, right? I do spikes immediately after I do ADRs. So after I do ADRs, architectural decision records, it means I'm making decisions. So then what I want to do is that I usually do a spike wrong to say, okay, there's some decisions that we're not so sure about, that we don't know if it's going to work or not. Let's just do a quick test. So those are called spikes, right? It says four properties are non-negotiable. Owner the controller right state. That is true. I like that. So workers have no path to mark its own node path and no right access to the state store. This is awesome. This is the rule in agentic code. Like, I'm going to be geeking out on this. This is actually pretty interesting. I love that. Let me. Hey, that's the crazy thing, man, in life. Like, if you do have to listen to people who are gonna judge you while they're not doing anything themselves, you will never do anything in life, right? So, yeah, I might appear to be a clown that I'm talking to myself, but hey, man, you got to start somewhere, right? I do this consistently. I'm doing real engineering work. People will stop by, right? And plus, I'm doing this for myself, right? I actually build out the system, so I'm gonna be here doing this anyway. Might as well stream it, and hopefully, if I'm able to help this one person, that'll be great. So, what was that Dana Brown or Dana Brown? Hey man, if I'm a fool for I'm a clown for doing it, and that's what you feel, I hope that you never have to start something from scratch in your life, man. But if you do, I'll be there to support you if you let me know about it, right? So basically, it's kind of like jumping in. So owning a control right state. This is actually good, and as I was mentioning before, I wanted to just respond to the whole comment. Um, this is a very important engineering principle. You have to get tools to your LLM, right? And especially you want to get those tools. And in this case, you can't have an LLM that actually writes its own code and then has access to write into the state store that it could possibly say, hey, I'm done, right? So you cannot give it that tool. You cannot give it that access. So workers will have no path to map their own node past and no right access to the state store. So basically, they don't have the ability to change anything in the graph, and they don't have the ability to change anything in their store, right? So validators are declared before work begins. So that's actually pretty cool. I remember going back and forth with the LLM about this as to when the validators or the test loops are to be written. So where we landed was that they are going to be declared before the work begins, right? So in the node contract, it's going to be produced by the planner. A worker cannot offer, weaken, or select its own acceptance criteria. So that's basically simple, right? So if you have a sub agent that's going to do some work, it cannot write its own acceptance criteria. Like I know some people like to do this, right? They'll tell the LLM, like, hey, go ahead and do this and work on this. And hey, the same LLM, you'll say to the LLM, go write the integration test. Sorry, the unit test. You cannot do that. The LLM is most likely going to cheat, right? Or people will say things like, hey, I want you to go code this, right, with the goal of getting it completed. Oh no, by the way, I want you to also write this test and also test. What do you think the LLM is going to do? It's going to write the test that's going to allow its code to pass. So what we're saying here in the engineering runtime is that the worker cannot offer that. It has no input to it, and it for sure cannot write its own acceptance criteria. That is actually done by a planner, which is independent, doesn't share any context with that worker. So a worker does not offer the gate that judges it. Same thing here. When a gate requires a new test code, and that's done by the planner, a different worker writes that code. Declaring the validator is not sufficient. If the implementer offers the test, the validator runs, the gate is a mirror, and everything above is decorative. That's a very fancy way of saying that if the sub agent that's implementing the code is the same sub agent that offers the validation runs, then the gate that is created is just a mirror. And that's what I think I was just saying. And if you do that, then this whole system is just decorative. The next thing is that evidence is durable and reproducible. So a claim of past that cannot be derived from the stored evidence is not evidence. Right? So basically what it says is that if there's gonna be a claim that the test passed, there has to be enough evidence also stored or information also stored that if you want to rerun that test, that it will also say passed. Because if not, then that's not durable evidence. So durable evidence is evidence that is stored within context, with enough context that if you want to do a replay, then you're going to actually have the same deterministic outcome. Then it basically says like, look, here's all the alternatives that we actually considered as well. So let me just check something here real quick. So one of the things I want to show is that I think I have another diagram, which is a gate triangle. Let me see this. Again, remember, my system generates me diagrams that I can actually go ahead and look at. This kind of help my understanding. So let's check out this new diagram that got generated. So this is it. Agents Act Evidence Advances, right? So I have a worker, uses call dash P, right? So it's out of process, it's working. You have a node that's going to verify, right? The controller runs the declared validators, right? In its own process. Only it can actually write to state. If all pass, the node is passed, and then downstream unlock. So the graph, it now says this dependency has been met. It can actually move on downstream or to any next. It can traverse the graph right to the next to its next stop. If it doesn't, and any required validator fails, the node is become the test node becomes retriable, right? And the yeah the the node itself becomes retriable. So every retry must vary at least one input. So it basically says like, look, if you're gonna retry it, you just kind of retry the same thing. Something has to have changed, which is really good. Nothing downstream moves. So the blast radius is one work tree. This is what's super important, right? I want to go back to another diagram that we had because I think this is hitting me really in the place where I want it to hit. So let me see. I think I had another diagram here. Was it this one? I guess this one. Yeah. This is a good one for us to look at, right? When you look at what that means in terms of blast radius. Right here, if we look at sequential, right, we talked about this. Node A, right, was a sub-agent doing the first step in the process. Let's say it was wrong. Node B would be wrong. Node C would be wrong because they're all like, right, feeding off each other. The blast radius here is all free. Something wrong, it affects all three. Let's look at it in parallel. If this was wrong, and then we went out and we found out all this will be wrong. 1, 2, 3, 4, 5. Blast radius is all 5. If this is correct, node B is wrong. Node C could be correct, D could be correct, E could be correct. But then the convergence is actually going to be incorrect. It means that the blast radius is this, this, and this. But the problem here is that even if node C, D, and E are correct, the outcome is actually wrong. But at the same time, if you do it properly, right, you can see the blast radius is less, right? But at the end of the day, if node A is wrong, the blast radius in both is the same, right? So not to be too confusing here, but all it says is, look, we don't have this kind of deterministic retries and all that kind of stuff to gate before next actions are done. The blast radius is crazy. Now, I want you to understand what also happens here. Let's look at this, right? Understand this. With this architecture here, we're not saying that the worker does its job and then dies. We're saying, no, this is going to have a loop. And I know we've all been talking about loop engineering and loop, all right, loop instructions and all that stuff. This is it right here. This is the loop. So if the worker is wrong, it goes through the node verifier. The controller runs the declared validators. If it's wrong, it says, hey, I'm going to try to fix at least one thing. It comes back here, right? The worker does it. It goes through the process again in a loop until it gets to a point where it says, oh, all has passed, and then it moves on. So it's the difference between, hey, I have 50 agents that need to run because I have 50 different work units I have to actually build out. It is a difference between, oh, this is going to take 5 hours to do if all of them were just correct, right? Versus, oh, this is going to take 8 hours because as I was going through this, certain workers got it wrong the first time and had to enter a loop until it gets done. And if you look at this, you might say, well, Chris, when does this loop exit? Well, practically, you can put a limit on the loops, but understand if you put a limit on the loop for any worker that has a dependency to other parts of the system, the others don't get done, right? So the engineering runtime, what it's going to do, it's going to keep a track of token usage because I built it for Claude Code. I'm building it for Claude Code. It's gonna understand and try to make a best guess, right, on your usage. And if it can continue within your window, it's gonna continue just kind of trying to loop. Because at the end of the day, your window for I have the 200 max. So my window, right, resets every 5 hours. So if I go to bed at 12, I usually get up at like 5. I'm working within that window, right? So it knows what it. And remember, I said we try to make every worker, the work unit it works again, to be done in about 100,000 tokens. So it means that that thing can loop quite a bit to get a worker correct. And look, at the end of the day, I rather get a worker correct than have a worker be half-assed and then go on to do like a bunch more workers in its dependency graph that are all going to be wrong because that worker was wrong. At that point, it's just feeder, right? You're not really finishing because you have to go back and do everything over anyway, right? So so this is what this actually gets you. All right, so let's see. I'm nearly done here. So this is good. I'm not seeing much stuff to change, which is actually interesting. I think I had such a long conversation with the AI that I think it got this one really, really, really good. Really, really, really good. Now let's look at alternatives. Right? I usually do a diagram for alternatives as well. So I'm pretty sure there's an alternatives diagram in here. Where we at? Where we at? Oh, yeah, go. Alternative gates. Let's see what that looks like. Alternative gates. Yeah, I don't think the diagram makes much sense. So let me just look at this. Trust the agent's completion report. Rejected. Right? This is the whole reason we actually created this. Next one is use an LLM reviewer agent as a gate, which is what most people do. People will like, hey, AI, just review this and test to see if this is done. So what we did was that we rejected it as the primary gate. Look at the word primary here. So this is interesting. It replaces one probabilistic judgment with another, which is what I said, right? You can say a primary gate for an LLM completing its job is another LLM that's probabilistic, right? Even if they don't share the same context, right, where it doesn't really necessarily lie, there's still a probability that it is wrong when it reviews stuff. Right? And then and that's the other thing. Correlated model errors mean the reviewer often shares the implementer's blind spot. What that means is that, look, if I'm using the same model that used to write the code, used to judge the code, then that might still have a blind spot because the reason for the failure might just be it's the model. So at best, you can maybe use different models, which some people do, but look, at some point they still share something beneath the engine, right? So again, it's probabilistic, it's correlated model errors, but it does say that an adversarial reviewer is valuable as an additional node where judgment is genuinely required, but it never substitutes for executable verification. That's a very nice word Smith sentence here that basically says it says an adversarial reviewer. What an adversarial reviewer is basically an LLM acting as a red teamer, like a red team member. But it's saying that you can do that, but only if it's additional and only if it's generally required for high reasoning tests. But you can never substitute for an executable verification. And the executable verification here is a deterministic node that says I am going to execute this code and this actual test plan. The other thing we said is to validate on and integration boundaries. Rejected. Yeah, I'm glad we rejected that. And that's what we talked about the blast radius, right? It lets a broken node's output propagate to several downstream nodes before anything notices, right? And I kind of showed that a little bit early on, right? Where you go from node A, B, C, and D, and if A was wrong, your blast radius is all these 4 nodes. So, and then integration would be like when we bring all the information together in a sub, like when we do a sub agent parallel fan out architecture, right? Integration is when you bring all the nodes back together after you fan them out, right? So what it's saying is that if we actually do the validation at only the integration layer as opposed to the individual unit, right, the work item, it says by the time that you do that, you've affected several downstream nodes before anyone notices, right? And you are going to you want to maximize rework. For those of us that don't know, in software development and anything service based, like too, like anything where there's work to be done, rework is 70% of the cost. This is like a Six Sigma number, right? So basically, what you're saying here is that if I validate only when I try to bring things together, then what I am for sure doing is maximizing the probability that I'm going to have to do rework, right? So a cheap per node gate catch failures while the blast radius is one work tree, right? Which is what we actually decided. Then the other one was let the agent run the test and report the results. We rejected that. We know why. Trusting the runner's exit code, we rejected this. We kind of talked about this. So then this is the decision. All this kind of looks well with me. And then the last thing that it kind of looks at is let's look at the consequence. And I actually have a diagram for that too. I actually like this. Let's see. Evidence course. So again, as I said, the my skill that actually does all of this, it creates a diagram for each pretty much each part of the ADR, as you can see, right? So one, we looked at like around 5 diagrams here. So it kind of creates a diagram for each part of the ADR so I can actually visualize it because it helps me out quite a bit. So let's look at what our pros and cons are, which is our consequences. So look at this. Let's see. So our decision, right? And again, remember what our decision was, right? Our decision was, oh, sorry, let me go back here. Let's see. I just want to actually say what the line is. Our decision is to take the agent's vote away so that it cannot judge its own code. Our decision is that we're doing test nodes, right? Our decision here is that two workers, like two sub agents, cannot be directly dependent on each other because a dependency for a agent is that all it's previously depended on, or all the dependencies before it from a testing standpoint is done, right? So basically what it means is that if agent B, sub-agent B has to depend on sub-agent A to be done, it doesn't directly depend on sub-agent A. It depends on all sub-agents A validators, right? And those obviously are constituted within a test node. So it's basically saying that sub-agent B is dependent on the test nodes that actually contain all sub-agents A's validators, right? So sounds very complex, but it's not. It's just basically saying that you cannot go from one sub-agent to another in a dependency graph. It forces the relationship to go through the test nodes. That's basically what it is. So that's a decision that we made. And then based on that, we see what it actually buys us in terms of value. It says downstream cannot unlock on an unverified claim, which is good. So that's the property that makes the fan out safe rather than reckless. So remember at the beginning, if you look at the beginning of the stream, I was talking about how sub-agent fan outs are reckless without this, right? So failure services at the node that caused them. So that's actually good. So the work tree and event log are intact for the diagnosis. Done gets a precise auditable meaning. So whenever we define done for an actual work item, right, it is precise. It is backed by reproducible artifacts, meaning that I can get up tomorrow morning and I can replay a particular test node, right? I can replay a validator in case I go like, did you really get this correct? Is this true? I can just go replay it because I'll have the actual information, the actual test information that was used. I have the actual outcomes. I can go run that myself. And then the last one is that prompt quality stops being a safety control, right? So a lot of people think that you can write better prompts to have the AI act better and not do certain things like cheat. That's not true. So at this point, it's not about prompt quality anymore, right? You're baking in your fences into the actual infrastructure, which is the graph and the test nodes and all that kind of stuff. So again, you can see my AI when it wrote the architectural diagram, it says this is the one that people underestimate, is that prompt quality is not a safety control. You can't rely on prompts to actually keep your system safe, right? Or keep your AI from doing stuff it's not supposed to do. You cannot be like, hey, go write this code, right, for this work item, right? Here's the thing that I want. Oh, and then run a test. And by the way, do not cheat. It's not a safety control. You have to build a safety control into the environment, into the runtime that your agents are running in. And that's what we did. So what does it cost us? It means that if we're going to do this in our engineer runtime, every node needs meaningful validators at plan time. So a node that isn't mechanically checkable is a planning defect. It that means is that since every node, every worker node is going to work on a work item. So again, I'm talking from a Kanban perspective, right? So you have a work unit, you have a small story that you need to do, right? Like write this function, or it could be write this API endpoint. What it's saying is that every node needs its validators at planning time. So in the engineering runtime, there's a command that's going to be called /plan, and that's when it takes all the information from the ADRs, the PRDs, and the specification files. It's going to take all of that and it's going to create the graph. So when it's creating the graph, part of what creating the graph is going to entail is writing the deterministic checks, the test plans, right? So it says that if you have a work item that cannot have or that does not have a meaningful validator at runtime, then it's going to throw an error. No, I don't expect that to happen, but you never know. But I believe what's going to happen is that that's going to be end up being a test for the LLM. Because remember, the LLM is the one writing the plan. So basically, it's going to be a check to see if the LLM is actually following the rules that it's supposed to be following. It says validation cost wall clock on every attempt. And what that means, wall clock, is just means like, hey, the time it takes to do something, right? And that's the true value of when people say they're running things in sub agents, right? In a fan out right now, is that they can run 50 of them at the same time and they get up, they go away for an hour and a half, and they come back and stuff is done. If you're validating, you're going to affect clock time. And I kind of mentioned this early on, right? That if something fails and you have to retry it, right, and it is a dependency of another work item, then the other work item is not done. So you'll come back an hour and a half later and you go like, oh my gosh, I'm only 30% done. But here's the thing, you're 30% done, but if you did not have these validations and you came back and the code was completed, then you start looking at it and it actually is not complete because it was incorrect because your blast radius was so big when one thing went wrong. You then have to QA, you have to review, then you have to rerun it again. In the long term, it takes longer. And that was my point from the beginning. That's why you need to have validation. Whether you're doing stuff sequentially or you're doing a fan out structure, you need to have validation. Some valuable work has no executable test. So, for example, UX flow, an architectural proposal, that's going to fall back to human approval. That's okay, right? We already addressed it in ADR 15, it appears, right? The system is only good as the validators. Now, this is the one that's going to really jump out to me, right? It's going to be super important when I design this to be able to write this test nodes properly, because if you this whole thing relies on the test suites being perfect. Well, I should say as perfect as possible. Now, one of the things I think I'm going to do is I'm going to borrow some stuff from test driven design as well as some stuff from Agile, where I'm going to do like scenario based acceptance criteria. And scenario based acceptance criteria is one of my favorites because what it does, it allows us to lay out all the scenarios, right, that might be associated with the work item that you have, right? And I'll give an example. If a work item is to help me log into a system, an API endpoint that lets me log into a system, scenarios would be, and the scenarios are also always written in a given, when, then format. So you say like given, that someone has not valid against the system when they provide a username and password, then a 200 should be issued with a token. Then you can look at all the different scenarios, right? What is a scenario where they give you the wrong username, the scenario they give the wrong password? You look at the scenario where they've tried to do it 10 times in a row and it was incorrect, and all those things are scenarios. And the reason why I like scenario-based acceptance criteria is because LLMs, because their reasoning engines are really good at coming up with scenarios. Like, right? So if you tell an LLM to write you a test for something, it might get it wrong. It might miss stuff. If you tell an LLM to reason with you and give you all possible scenarios as step one in a chain of thought, it's going to most likely be correct. It's going to come up with way more scenarios than you as a human can actually pick up. Right? So that's one thing I'm gonna actually come out here with. And I'm actually gonna communicate right now to the LLM. All right, so let's go back. I'm gonna actually say, hey, this is actually really good. Hey, I am reviewing ADR4, and it occurs to me that to ensure that we get really good test suites, that we adopt acceptance based, no, we adopt scenario based acceptance criteria. Here is my reasoning. I think that, I should be using Whisper for this, but I'm on the live, so I don't know how that will actually work. I haven't tried it yet, so I think that an LLM which is creating the test would be better at first imagining all plausible scenarios as a step in chain of thought before writing test. Red team this idea. Right? So I'm just gonna red team this idea, which means I'm just gonna have the LLM attack it to see if I'm wrong. It's a really nice way and a really thorough way to kind of say, like, look, don't just agree with me. So instead of just saying don't agree with me, just basically saying, like, look, red team this is something that makes the AI more adversarial, right? Because if you say disagree with me, hey, just don't be a cheerleader, what's going to happen is that the AI is still going to be polite, right? But if you tell it the red team, it's going to actually get into it's going to take on a red team persona, so to speak. It's going to be very adversarial. It's going to really poke holes into this, and it's going to see if I'm right or wrong. And if I'm right, it means that we just got like a really big piece for the engineered runtime, which is going to include two things: accept scenario-based acceptance criteria, and no, I'm explicitly saying that the creation of the test suites should use chain of thought. So basically, it's right now it's reading the ADR. It's like, okay, cool. I'm gonna read the ADR. And then it's so when I said see what I was saying at the beginning of the stream, I said it's going to read the ADR, and not only that, because my ADRs are linked, it's also going to read the associated ADRs. See, it's reading 20 and it's reading 9, which is what I wanted, right? So you say, hey, see that it says 9. It's so from what I've asked it, it's deemed that 9 is important to do, and then I think ADR 20, which I think is mentioned somewhere in here, is also done as well. So it says that the short verdict from the red teaming says that the failure mode you're aiming at is real and is the one ADR4 explicitly refuses to solve. But as stated, the test right LLM imagines all plausible scenarios as a COT, chain of thought step. The idea fails on the system's own spine in three places, and one of them makes things actively worse rather than merely not better. There's a version that survives. It's at a different place in the pipeline with code supplied structure. So basically, again, that's what you ask it to write to. It goes like, nah, dude, I don't like your idea, but there's something about your idea that I like. So let's look at this. Oh my gosh, I'm not reading the whole thing. This is gonna be too long for me to understand. Attack one, as stated, it reopens the exact hole ADR 20 was meant to close. So apparently there's an ADR 20 that goes like, hey, I don't like this. And just by reading the title, the name of that file, test authorship separation, I know what it means already. I think it literally means that if you do that, the same thing writing the test is the same thing writing maybe the the work units. I don't think it's talking about the code. So let's see what it talks. Values are declared before work begins in a node contract produced by the planner, the work, blah, blah, blah. So if the test node imagines the scenarios, the test node offered its own acceptance criteria. Its gate, the red check, would then be valued against the scenario set the same worker generated. Okay. Attack two, it multiplies the one defect with no defense anywhere in the system. This is a serious one. The red check proves a test detects the absence of implementation, but it does not prove that the gate detects wrong implementation. That's good. That's good. So a wrong scenario doesn't merely fail to catch a bug, it can actually manufacture one and gets the full evidence chain to bless it. Interesting. Attack three, all plausible scenarios is a completeness ship signal. A model asked to enumerate all possible plausible scenarios emits a list of roughly 7 to 12 items. That cardinality is a property of list ship generation, not of the domain. Yeah. Attack 4, it degrades the red check rule 3. Attack 5, retry pressure runs the wrong direction. So it says based on all these two things are generally right and worth keeping, the target is real. The failure class breadth beats happy path generation. The rival you should wait against. So it says the net advice is adopt, but dude, that's what I meant. That's what I meant. I didn't mean for you to write it in. I didn't ask you to write it in the test node. I was saying that the planner should write it. Yes, that's what I meant, dude. Okay. We landed at the same place. Because to be clear, I was thinking that the planner was the one who did it. Are you saying that the planner is not LLM? I think that's what it's saying. Interesting. Oh, I know what it's thinking. It's thinking that during the planning stage, the planner is human driven, or at least human guided. Yeah, it's checking. It's checking. It's checking. Let's see what we come up with. This is actually good. This is why you do ADRs, right? This is why you do ADR reviews, right? Because again, this is a big deal. I'm loving this. So let's see. Let's see. I'm pressure testing the LLM here. So the planner is a model, and the ADR said so in many ways. The planner is a model. Oh, and it says that ADR4 already said that a model's claim about its own output is not evidence. So this is going to really meta, right? I've always focused on this as the saying that the model that is used to actually write the code, right, the subagent, I've always said that that cannot actually judge its own self. What the red team is saying is that no, it's not only there that you have to keep that rule, you also have to keep the rule in the planning stage when you're using a model to create the scenarios. Because if the model is used to create the scenarios, then and you have the model saying like, hey, this is good, then you have actually done the same thing that you're actually saying that's not good in the writing of the code. And there's no deterministic way to test that model that actually does the scenario planning. Hmm. That is good. That is good. So I think I know how to actually fight that. So I'm not going to read all this because I think where I'm going to go already with this and ask it if this is a better idea. So, what if the planner is an interactive or human in the loop process where the LLM creates the scenarios, but the human must approve? I think that's the answer. And usually AI tries to overcomplicate things, right? And that's why I didn't read all that it wrote, because I'm like, if you're writing all this, it means that you've already missed the plot, right? Because the simple answer is this: have the planner be an LLM, put a human in the loop, right, which is me. So the planner goes like, hey, here's the scenarios that I see, and then the human goes like, yes, 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 no, tweak this, right, or that, or let me see if there's anything else. So it's basically, yeah, human gates. So let's see what it kind of comes out there from here. And also, this is the only part of agentic coding that I actually hate, which is waiting for the model to actually respond, which is usually why I'm doing like 10 things at a time. Which is the reason, part of the reason why I'm building this whole thing, because I just can't sit and watch code generate, man. I can't do it. But the one way you can actually get to systems where you can actually YOLO is if you have really good systems that are going to give the same output in terms of correctness as if you were sitting a babysitting it, you know? And all this is to answer a very simple question. Good news, first, you're not inventing it. Actually, in ADR 15, it already says changing acceptance criteria as a mandatory human node. Scenario sets are acceptance criteria, which is what I told you. So offering them underneath human approval is already policy consistent. And at plan time, it costs nothing against the unattended run thesis, which is what I just said. The whole thesis I have is that the execution of the agents, the sub agents, when it comes to write the code, that's what I want to be autonomous. Everything before that, I want it to be human involved because that's your quality gates, right? Your quality gates is a human saying that, yep, this is true. Yes, this PRD is correct. Yes, this ADR is correct, right? Yes, the specification file is correct, right? Yes, this test file looks good. So I was already saying this. So it's basically saying like, you know what, you're right. And at plan time, it costs nothing against the unattended run thesis, which is the thesis that the robots actually, the coding agents have to run their own. And it's front loaded before build, right? See that? That's what I just said. Because build, correction from earlier, build is what actually builds out the DAG, the graph. So you go plan and then you go build. So in the planning phase, human in the loop, which is me, looks at the scenario the LMs have generated and go like, yep, approve, 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 change, approve, 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 reject. Okay, everything is good, slash build. So apparently we had an ADR that actually predicted some of this. Approval fatigue. Man, I love ADRs. That's why I say when you have conversations with the LLM and you put them in the ADRs, the LLM picks up everything. Because I think apparently, because I'm just talking to the LLM, as I said, right when I want to build. Apparently, I thought about this before because you can see it says, "Hey, ADR 15 already says approval fatigue is a general risk. Too many human nodes, and the user will just rubber stamp them because we all do that. Like, I might have been a little bit guilty of this yet today. Like, I go like, I'm not reading this, right? The only thing is I didn't approve it, right? So it is worse than not having them because it produces record approvals that mean nothing. Placement must be deliberately sparse and reserved for genuine consequence. So basically, all it's saying is that, look, yeah, it's great to put human in the loop, but if you have to approve too much, there's going to be a fatigue, and not only is going to be fatigue, and it's worse because now a human is approving it, and there's evidence that they approved it. So it says like, look, we have to be very careful with human in the loop, not too much. This is why I disagree with this. I'm going to tell that I disagree with it because I don't believe there should be approval fatigue. Because if you're writing code that actually means something, you should at least have the decency, the wherewithal, the need to do a good job. To go like, I have sub agents or I have agents that are going to write me a million lines of code. The most I can do is spend the 6 hours making sure that I set up the test properly. I don't believe in this. I am not building the engineering runtime for people who are lazy. I'm not building it for people who want to take a shortcut. I'm building this for people who actually want to deploy production level software, but still get the speed and the capabilities of an LLM. And I'm going to tell it that. Yep, yeah. But here's the thing. One, I am not indexing for people who do not believe that writing proper tests important. I am writing this for serious developers who are developing production level systems. I do not care about approval fatigue. Two, I do not see login and evidence of approvals as a bad thing. See number one. Yeah, like this is not who I'm developing the system for. I'm not developing this engineering runtime for somebody who wants to YOLO, right? And kind of sit here and spend 2, 3 hours approving tests. Like we're not doing this, right? This is for serious developers who are right. And when I say serious developers, I don't mean like trained. You don't have to be trained, right? It could be someone who's just, hey, I'm not an engineer, but I have this runtime, and this runtime is gonna guide me for this. It's gonna be like, hey, here's the test, here's the test, here's the test. Can you approve? Like that's who it's meant for. I'm not. This is not meant for someone who goes like, oh, make me diet at, make me weight loss tracking app, make 5 buttons, right? Uh, code, no mistakes. That's not what this is for, right? This is for the future for deployed engineer. This is for the person going like, look, I'm not an engineer, but I have some expertise in this particular field. I feel like I can build an application, but it's an application that has to work. Okay, I have this runtime. It's going to help me because I can talk to it and tell everything that I know, needs to be done, right? It'll create me my ADRs, it'll create me my specification files, it'll create my PRDs, right? It'll ask me questions about testing, and all I have to do is just talk to it and approve stuff. Yeah, this is who I'm creating this for. Okay, so you are saying in a long-winded way that a person may still miss something in terms of a missing test. One, isn't that true in like forever in traditional coding? And then two, we should have in some ADR a conversation on traceability audits. All right, let me just pull something back here. I think I talked about traceability audits before. Let me see. Yeah, requirements traceability audits. Okay, should be done in 5 minutes. I think this is the last thing I'm going to tell to, hey, update the ADRs to reflect this. Because other than that, we're good. So again, every time I do an ADR, that's what I hope that comes out of it, right? I hope that comes out of it is certain hole that the LM had when it created this, right? I usually don't like when I go for an ADR and it's just perfect. Like it usually means that I'm not thinking, and that's how I take it. Yeah, it says you're right. It's a permanent condition of the craft. And it says yeah, on traceability, a requirement traceability audit, and it says it's the actual answer. So again, if you ever follow me, you know one of the things I talk about. You don't have to be able to code to be able to be great at developing agentic composed software or applications. What you do need to be really good at is concepts, right? Concepts, systems, and designs. You see, the LLM, which is way more knowledgeable than me, didn't didn't think to itself that the way to solve all of this was a requirement traceability audit. It didn't think about that. I had to tell it, hey, what about a requirement traceability audit? Because it told me, it says, oh, red teaming won't be enough. This won't be enough. I say, look, man, just run a requirements traceability audit. And for those of us who might be looking at this that don't know what a requirements traceability audit is, it's you have red teaming, which actually looks at what you have and says, here's the problem with it. Requirement traceability audit, what it does, it looks at the situation that you're in, like in terms of what you're saying that you want to accomplish, and then it says, I am going to look at what you're doing and I'm going to draw lines between what you're actually doing, what you say you want to do, and I'm going to find gaps between what you say that you need and what you're actually doing. So that's what it means. It means that, okay, now look at how we solve the problem. LLM, chain of thought. Actually, let me just talk to it. Yeah, let's go. LLM, chain of thought. First part in the chain of thought, hey, look at all the, come up with some scenarios. Human in the loop looks at it, human in the loop approves it, right? Makes some changes. You then red team it, right? Well, the system red teams it. Then the engineering runtime red teams it, finds potential issues. You go back and forth, it's fixed. Then you go like, hey, let's run a requirements traceability audit. It says, oh, here's the things that you're supposed to do that you didn't do. You then add it. Once you add it, you red team it, and then you're done. So, are we on board to update the ADRs, especially for this in a nutshell? Planner is doing this. Planner uses human in the loop. planner uses chain of thought with with scenarios scenarios as a precursor to writing the test. Planner uses red teaming. Planner uses requirements traceability. Okay, winding down here is the last thing I'm gonna do. So it says yes, all five with two precisions and one open item. Precise on number three, which is planner uses chain of thought. Okay, awesome. Four needs this ambiguation before it can be written. Okay, I'm gonna ask it, agreed, do we think we need four? If we do, I am saying B, not A. Okay, and this should be the last thing here. And then we're going to just write to the ADRs. Looks like we're going to affect a bunch of ADRs. We're going to actually create a new ADR. We're going to actually update ADR 4, update ADR 9, 15, 16, 20, and 31. Again, this is a load bearing ADR. So, okay, do it. Love this. All right, so this will take some time to write, but this is exactly what I wanted out of this. This is maybe the longest ADR session. I want this to maybe go like an hour, but this one's pretty heavy because it's the load bearing ADR of the entire system. As you can see, a change affected like around 6, 7 ADRs, right? I don't fully expect that for the other ADRs, and I do expect these other sessions like these to be like an hour. I might actually even do a couple of these in one session actually. So I want to have you stick around here while 80 hours are getting written. Actually, this is it for me. I might just leave this running and call it a night. I think I have some Madden to go play to close out my weekend. And if you join, again, I just want to say thank you for joining me here on the stream. I'm new to this, so if you have any feedback, please let me know. Um, Again, I know these sessions can be pretty heavy, but I'm going to real engineering and reliability engineering conversations on right using AI. And look, whether you are someone who wants to become a forward deploy engineer, right, or work in agentic space, you want to follow. If you're someone who's in charge of, deploying AI agents, and AI into your organization, you want to follow. Hey, man. Hey, John, man, I appreciate you, man. It's always good to get some good feedback. You made my night, man. You made my day. You know, I do want to continue doing this, and as I say, I'll be doing this every day. By next week, I should have like a set schedule every day, and I'll send it out to the community. And again, if you have any feedback for me, any information, just shoot me a message. You can also find me on LinkedIn. If you look at my profile, send me a message here. I'm always willing and always open to hearing from everybody. So again, thank you all for actually jumping by, and I'll see you all tomorrow. Bye.